Hey everybody, in this video we are kicking off an entirely new unit. This unit is called Exponential and Logarithmic Functions, and we are going to break it into 4 sections. We are currently looking at section 1, which is exponential functions. We have a few examples to look at here. We will have 4 sections altogether, and I will be going through all of the examples, so all of the videos will sort of be labeled as being under this unit, and then it'll be section 1, example 1, section 1, example 2, and so on. So it'll be like S1E1. So it's going to kind of look like season 1, episode 1, but it's section 1, example 1. Kind of follow? All right, so let's go. So we're going to look at some word problems. We have been talking about exponential functions. We graphed them when we did all the parent functions. You talked about exponential functions in Algebra 2, and now we're just going to get into it a little heavier in pre-calc to kind of get ready to tie everything together before the end of the year. So let's talk about it. Now, the structure that we need to consider for an exponential function is as follows. We're going to primarily focus on the structure of y equals. Now, usually we kind of focus on y equals b, but I'm going to use capital B because lowercase b I use for horizontal stretches and compressions, as many of you know. So for now, I'm going to use capital B. Most books will use a lowercase b to the x, and that b stands for the base. Now, the base of an exponential is either going to be your growth or your decay factor. Now, how do I know which is which? Well, it's a growth if the b value is greater than 1, and it's going to be a decay factor if that b value is less than 1 and greater than 0. In these situations, our b value will not be negative. All right. Now, what else do we have to consider over here? Well, it'll never be 1 because 1 to any power is 1, and then that would mean the thing isn't changing. I mentioned here I wanted to talk about a little bit percent change. So just a few things to mention. If something is going up by, say, 35%, right? If something's going up by 35%, then that would mean our base will basically be equal to 1 plus 0.35, because you're keeping 100%, and 100 as a decimal is 1, and you're increasing by 35%. So the base that you're going to look at is 1.35, okay? However, if we're going to be going down by 35%, it'll work in a very similar way. It's not going to be a negative base, but your base will be essentially 1 minus 0.35, which will give us 0.65 as our base. And that's what I mean by it being between 0 and 1. So when you lose 35% of something, you are keeping 65% of it. It's more efficient when you're doing calculator work to multiply by 0.65 to get your total after the discount, or to multiply by 1.35 to get the total after the markup. Instead of finding the percent and adding it back to the original, instead just find 135%, or instead of deducting 35%, just figure out what 65% is and just go from there. Now, what else can we look at? Typically, we're going to have a little bit more going on with our exponentials than just this, right? We're really going to more or less look at y equals a times the base to the x. Now, what is this a value we mentioned? Now, while it's our vertical stretch or compression, that's true when we're talking about it in a graphical context with transformations. It's also what we can call our initial value, which should also correspond to the graphing, because that's where we would start our graph above the little crosshair, if you remember, that normally took place at the origin. It might shift based on h and k. So your a is your initial value. Did you start with $1, 1 cell, 1 bunny, 1 whatever, or did you start with 2 of them, 3 of them, 4 of them, and then it was doubling after that? So based on how much you start with, it's going to impact how much you finish with. That's the same with negotiating your future salary. You want to get your future salary when you start a new job as high as possible if you can negotiate it, because if you get a percentage increase year after year, you are basically locking in a certain amount of money earned in your lifetime based on that initial salary. Okay, so food for thought. Now, based on this little quick review, let's just quickly look at this word problem right over here. Example 1, evaluating an exponential function. The exponential function f of x equals 42.2 times 1.56 to the x models the average amount spent, f of x, in dollars at a shopping mall after x hours. So nobody likes to read a word problem more than once. No one more so than me. I hate having to reread. So I like to get everything I can out of it the first time. F of x equals, so I'm writing it down, 42.2 times the quantity of 1.56 raised to the x. Now, just using what we know, this here is essentially your initial value. This is how much you're spending as soon as you basically walk into the mall, okay? Now, that number right there, 1.56, is going to be, since it's greater than 1, that's going to be our growth factor. Because, like I said, it's greater than 1, and it indicates that it increases by 56% for every hour you spend at the mall, according to the word problem, right? So x is the time you spend in the mall in hours, right? And then f of that time, so f of 2 is how much you spend after 2 hours, f of 4 is how much you spend after 4 hours, and so on. And they want to know, well, what is it after 4 hours? So we're going to do exactly that right there. We're going to find the f of 4. You need to get really good at writing the left side of your equal sign, because that tells the full story. It makes it a complete sentence. 42.2 times 1.56 to the fourth power. Now, when you do this in your calculator, you must not multiply these two numbers first. God forbid. No. What you need to do is order of operations, we're going to do the 1.56 right here first, raise that to the fourth power, and then you multiply that answer by 42.2 for your final answer. So I'm going to do this on the calculator on my iPad over here. So that's going to give me 1.56. Now I'm going to raise that. So I'm going to hit the X to the Y button. Raise to the, I already forgot what it was supposed to be, fourth power equals, there's that number. Don't write it down and then round it. Leave the full beautiful number on your calculator screen. And then we're going to multiply that by, I think it was 42.2, but I don't have it in front of me, so fingers crossed. So 249.93. Was it 42.2? 1.56. Hopefully I did that all right. So we got 249.93. F of 4 equals 249.93. Now, what does the whole question say? What is the average amount spent to the nearest dollar? So what does that tell me? That means I need to round it without change, right? In this situation, please read directions carefully, because it doesn't always say that. Sometimes you round money, well, with 2 decimal places, like usual money, right? So that would mean $250 is the average amount spent after 4 hours. All right, so there's your final answer. Sorry, it's a little sloppy. $250 is the average amount spent after spending 4 hours at the mall. And there you have it. So I would definitely recommend that you make sure you can punch it into your calculator. Every calculator is a little different. Every calculator has a little bit of its own quirk. So you want to make sure you're doing it correctly. And that is our section 1, example 1, kicking off this new unit. And to see the next one, we're going to do example 2 and 3, have to do with some graphs. So 4 and 5. And we'll get into some banking problems after that. So if you're happy and you know it, thumbs it up. And if you're sad and hated it, give me a thumbs down. I don't really care. Questions, comments, concerns, feedback, whatever the heck, in the comment section below. And check the playlist. And bye for now. Adios.